Let's talk about single surface contouring. Let's talk about the single surface contouring capabilities of mapping contouring system. So why even worry about this computer contouring? In the olden days, if you were a geophysicist or a geologist, you could make your maps and never even worry about it. But today, you will use a computer, and you must not let your technical skills be compromised by the software that you use. So what is a contour line? It's a line that represents points of equal value, right? Mathematically, more correct would be to say it's the line of intersection of a surface and a plane parallel reference to a reference plane. And a contour map, that's the projection of a series of contour lines onto the reference plane, which is normally mean sea level. So there it is in 3 dimensions. Here's our surface, and there are the parallel planes that intersect that surface, generating contour lines. And there's the contour map, all of those contour lines projected onto one surface. There are 2 fundamental techniques that computers use in making maps: indirect or gridding and direct triangulation. Here's a sample data set. Let's talk about the steps that are involved in gridding. First, you select a grid, size, and origin, and there it is. Next, you select the neighbors of each grid node. There's many methods of selecting those, unlimited number of methods, but all the neighbors should be evenly distributed around each grid node, and only data points near a grid node should be considered to be neighbors. That works out well in this western region where the points are randomly oriented, but over here where we have a 2D line, all of the neighbors are on the same side of the point. Not good. Perhaps we could pick only a certain number of neighbors in each quadrant or each octant, and that would get around the problem of having all the neighbors on one side of the data point. Once we've got the neighbors of a grid node, what do? We interpolate from those neighbors to the grid node and figure a value at that grid node. And then we throw away all our original data and we go with the grid. So here's a sample data set. We're going to use it to contour using various computer systems and various algorithms within those systems. First we grid it. Then with Petra we make maps using closest point or disconnected features, or simple weighting with slopes, or simple weighting without slopes, or highly connected features, or maybe geographics closest point, geographics adaptive fitting, geographics triangulation polynomial, geographics weighted least squares, geographics weighted slope, or kingdoms cubic spline, or flex gridding, or gradient projection, or inverse distance to a power, or natural neighbor, or ordinary kriging. Remember that all of those maps use the same original data. So, garbage in, garbage out, right? How about good data in plus a garbage algorithm, and you get garbage out. Let's leave the gridding and go to the direct or triangulation method of making computer contours and computer contour maps. There are similar steps in triangulation as there were in gridding, different but similar. Of course, we have to select the neighbors of each data point. There is our data set, and there are the neighbors. Fortunately, once we've triangulated, we know who the neighbors of each data point are because they are the points that are connected to a data point by lines. We set up at each data point and we determine a slope at the data point based on the neighbors of that data point. And we do that for all data points. And notice that points on the convex hull of the data have no neighbors outside, only neighbors inside, so extrapolation is somewhat risky. Next, we take those original data points and those slopes that we found at each data point, and we pass a surface over that entire convex hull or region of map such that it's normal, such that it goes through each data point, is tangent to the slopes at each data point, and changes smoothly in all directions. There are no slope discontinuities. Therefore, some points on the map may be slightly higher than the highest values that we saw, or lower than the lowest values that we saw. Remember those? They used to cost $15, now they cost $450. But for each triangle, we divide the value between the high and low based on a linear breakdown, and we get a map that looks very angular and unappealing and as if it had been made by a robot. So what can we do about that? But keep your eye on that triangle that's shaded. We can take the bigger triangles and break them down into smaller similar subtriangles based on a division of 4 lines, which we call a smoothness of 4, or a smoothness of 8, or a smoothness of 16, or a smoothness of 32. And as we begin to do that, we begin to see curvature develop within the map. And the more smaller triangles that we use, the smoother the map gets. And finally it gets to where it's almost beautifully smooth. But if we look within any interior triangle, it is a straight line vector within any triangle. So there's the final triangulated contour map. Here's a clustered structure exercise, and this is difficult because we have clusters of wells and large open areas, wildcat areas, and so we have to honor all the data in the well areas, and we want to honor reasonably the data in the open wildcat areas, and we don't want to show any anomalies there. Here's a map that was contoured by a recipient of the Sidney Powers Medal. Here's the MCS map. Notice that it found the closure. That closure. Here are the various maps made by some of the systems using these same data. Notice anomalies are appearing in these maps. If you see anomalies like this, it means one of two things. Either it's a data bust or it's valuable information. Once you get rid of the data busts, you have valuable anomalies. These are not true anomalies. These are simply mathematical errors. Here's some geographic maps, and notice none of the gridded maps find the closure. So here are the pertinent points about gridding. You must do a lot, and you can never guarantee honoring all the data points. With triangulation, you always honor every data point. There's advantages of hand contouring, advantages of computer contouring. I go with triangulation.